Hello and welcome to the second recording on the blog is Machines from Chapter 10, Section 2. What is a machine? Well, it makes tasks easier. It eases the load by changing either the magnitude or the direction of a force as it transmits energy to tasks. Take, for example, simply changing the tire on your car if you had a flat. Think of all the simple machines that must come into play as you work through this exercise. Working with your hands is challenging. These machines make that task easier. You have the wheel and the axle that you'll be addressing to replace the tire. You must use a wedge to block the other tires so the car can't roll. The lever, whether it's to remove a hubcap or to raise the jack, is easing the force that you have to exert to do the work. All of these terms will come into play as we explore the use of simple machines in our everyday lives. Simple machines, and we've seen several examples through our academic career, include the wedge, the wheel and axle, the lever, the inclined plane, the screw, and the pulley. Simple machine is made of very few moving parts. What makes them work? They reduce the amount of force per unit time that is needed, and so they simplify your task. Sometimes it's not the amount of force, but rather for a pulley, think of perhaps a direction of force. When we conceive of the complex machines that is a modern car or copy machine, these are actually simple machines that are added together. They consist of two or more simple machines linked, so that the resistance force of one machine becomes the effort force of the second. Added together, simple machines make compound machines. Now we must consider mechanical advantage. We will begin to quantify how the simple machine makes the effort easier. To address these issues, we think of effort force as our first term. This is the force you exert on a machine. The resistance force is the force exerted by the machine. Think of a fulcrum and a lever. This is a long bar and a point on which to rest the bar, as if to, say, raise a boulder, lift a rock, lift something. Like if you had to get a car up off of a person or something, you're going to use this fulcrum. Now, the force that is used to lift the car is the resistance force. If it is near the fulcrum point, it will travel a relatively short arc, a short distance. But your end of the lever can travel a great distance. And because you're moving it a greater distance, each portion of that motion is easier to perform. This is the mechanical advantage of something such as a fulcrum in the example given. It is the ratio of the resistance force to the effort force. This type of thing typically must be measured. Another example of the same type, and we've seen it before demonstrated in class, is to think of the torque that must be exerted on a simple door. It is best described by a heavy door. If you were to walk to the door and push near the hinges to close it, it is very difficult to move. Yet if you move your hand toward the end of the door, toward the knob, and close the same door, the effort is relatively easy. You're moving that door your arm is traveling a greater distance, but the amount of force you have to apply per unit distance is much less. This is the advantage of simple machines. You could try this on your own if you wanted to pause and try it with the door. Moving on, we will now address how we will quantify all of these different phenomena. How we are going to put numbers with the advantages that we find in the simple machines. The following slides will show us how to perform those operations. A mechanical advantage of a machine can be written a different way using the definition of work. If we go back to our learning before, we can think of work as energy. What we discussed last week, we equated work and energy. If energy cannot be created, the amount of energy that's going in, or the amount of work that is going into the system, must be equal to the amount of work that is put out by the system. Here we see the equation W naught equals WI. That is, work output is equal to the work input. Another way to write this is the force of resistance times the distance of resistance must be equal to the force effort times the distance of effort. Think once again of our fulcrum. The distance that far end of the lever travels times the force that you're putting in must be equal to the distance times the amount of force that is happening near the pivot point. Work sub 0 is output work, work sub I is input work. These must remain equal. If we were to describe an ideal machine, that would always be true. The work out and the work in would be ideal. The distance of effort divided by the distance of resistance would be equal. And the ideal mechanical advantage would be 1. But in all real machines, this is not so. The ideal mechanical advantage is not always 1, or the mechanical advantage is not always 1. So we must have the ideal situation to compare the true mechanical advantage to. If we do so, we can then describe it as a percent of how ideal our real situation is. The true mechanical advantage divided by the ideal mechanical advantage times 100 gives us a percent of efficiency of the machine we are exploring. The closer that is to 100, the more efficient the machine is. If we are discussing it as a ratio of output of work to input of work, we would again hope that output was close to the input and would again be 100. This is not always the case, and that is why we have to describe the efficiency of a real machine as compared to an ideal. The ideal of the ideal mechanical advantage, where the distance of effort is equal to the distance of resistance, and the situation where we think that the work in will always be equal to the work out. That is an ideal that we are looking for, but as we know, in the real world, there are non-conserved forces. A less efficient machine has a small mechanical advantage relative to its ideal mechanical advantage. Therefore, the percentage of efficiency would be less than 100. The mechanical advantage of compound machines is also able to be calculated. It is the product of the mechanical advantages of the simple machines it is made up of. We can add the mechanical advantage of each machine in series to give us the overall mechanical advantage of the compound machine. This has just been an introduction to what we will see as we work with simple machines and attempt to quantify the work in versus the work out. We will use the efficiency numbers to describe how well that machine works. And we will look further at the distance relationship to the distance effort. How much effort we must put in over what distance to make a machine advantageous. We will look at some example problems in class, and we will be able to describe better how these machines can be compounded to give us a greater advantage. So until tomorrow, or when we get back together, try a couple of these from chapter 10, and we will have several example problems before we start our independent practice in class. Thank you very much, and I'll see you there.